Hello, in this video we're going to take a look at a new idea, the antiderivative. Like the derivative, the antiderivative is very useful in solving problems in science, mathematics, and engineering. In fact, we'll study the antiderivative for the rest of this semester and for most of Calculus 2. You'll see it solves some very interesting problems and is a very powerful technique for problem solving. So let's start with the following question. There is a function f for which f prime of x, the derivative of capital F, is 2x minus sine 3x. What is f of x? So you might think about this for a moment. Can you write down a function capital F whose derivative turns out to be 2x minus sine 3x? And with a little thought you might come up with this answer, that capital F of x is x squared plus 1/3 cosine of 3x. This is not a hard answer to check because all we're claiming is that the derivative of capital F is 2x minus sine 3x. So one easy way to check this is to just calculate f prime for our proposed f and see if we get the answer up here on the right-hand side. Okay, and that calculation is done right down here. There's the derivative of capital F, and we have 2x plus 1/3 minus sine 3x times 3. This term comes from applying the chain rule to the cosine of 3x, and then 2x, that simplifies to 2x minus sine 3x. And this agrees with the right side of 1. So in this case, we say that the function x squared plus 1/3 cosine 3x is an antiderivative of 2x minus sine 3x. So the derivative of x squared plus 1/3 cosine 3x is 2x minus sine 3x, and hence that an antiderivative of 2x minus sine 3x is x squared plus 1/3 cosine 3x. However, there are other possible answers. Any one of these three listed here could work, and you see they differ just in this term here added, which is just a constant or a real number. And of course, if you differentiate any one of these three, you still get the answer 2x minus sine 3x back because all these constants down here differentiate to 0. Okay. So this tells us that a function really has many antiderivatives, and we can add or subtract real numbers as we did here, that is constants, and still have something that differentiates to the desired function. So because of this, we say the general antiderivative of 2x minus sine 3x is given by x squared plus 1/3 cosine 3x plus, we usually write capital C, and the capital C here is called a constant. In fact, it's called the constant of integration. The constant of integration. So we're going to see it's important to include this plus C when you do an antiderivative problem. It does have implications in physical problems that we'll look at later on. So we have some symbolism or some symbols to help us talk about this kind of problem. We write the antiderivative relationship in this way, and we can read this in a number of ways. One is to say the antiderivative of 2x minus sine 3x is x squared plus 1/3 cosine 3x plus c. We can say the antiderivative or the general antiderivative, either one of those is okay. We can also read one by saying the integral, in particular, this sign is called an integral sign. We can say the integral of 2x sine 3x with respect to x, that's what the dx tells us, is x squared plus 1/3 cosine 3x plus c. In reference to 1, the integral on the left of the expression is also called an indefinite integral, and we'll start studying definite integrals in chapter 5. So we will see the counterpart of this. Now, for each of the derivative formulas for the elementary functions, we have a corresponding antiderivative formula. So we spent a lot of time learning derivatives. Again, you know a lot of derivative formulas. For example, just to pick one, if you have the function 1 over k tangent kx, where k is a constant, and apply the derivative, the chain rule says you differentiate the tangent to get the secant squared, and then times, and you evaluate that at the inner function kx, and then you multiply by the derivative of the kx, which is k, and that knocks off the 1 over k out in front. So the derivative of 1 over k tangent kx, when k is a constant, is secant squared kx. Now, anytime we have a differentiation formula, we have an antiderivative formula, so we can kind of rewrite this relation down here, saying the integral of secant squared kx dx is 1 over k tangent of k, this should be an x here, plus c. We can also read this as the antiderivative of secant squared kx is 1 over k sine kx plus c. So these important elementary derivatives are given in the table on page 281 of your textbook, where each is paired with its related differentiation formula, and these are well worth knowing. Here's a picture of that table, or part of it anyway. So down here on the left of each column, you see an elementary function. We have powers of x, the trig functions, sine and cosine, familiar answers, secant squared, cosecant squared to these problems, to these differentiation problems. And then over here, the antiderivatives for the things in those columns. So you literally have to know derivatives backwards and forwards. Most of the things in this table are worth remembering or memorizing. We've encountered all of these derivatives at one time or another. I would like to add a 14th entry here, very easy one, that if your function k is a constant, then the antiderivative is just kx and then plus a constant c. It's because we know if we differentiate something like 2x, we get 2 back. Minus 1/5 x gives us minus 1/5 for the answer. And so the antiderivative of a constant is one worth noting too, although that kind of is included up here in item 1. So when we studied differentiation, we first found the derivatives of lots of the elementary functions, exponentials, logs, powers of x, the trig functions. And then we derived rules like the product rule, quotient rule, chain rule to help us differentiate more complicated expressions formed by combining the elementary functions. The situation for antiderivatives is very similar. Again, the table on 281 gives the antiderivatives for several elementary functions. And during the rest of this semester and in a good part of Calculus 2, we'll learn how to work with more complicated expressions formed by combining these elementary functions. Now, one of the most important and easiest rules to apply is the rules for linearity. We had such rules in the derivative rules also. They say this, that the antiderivative or indefinite integral of a sum of two functions f and g can be found by computing the antiderivatives of each of them separately. And the analog here is that when you do a derivative of a sum, you can write that as the sum of the derivatives. Likewise, constant multiples, so here c is a constant. Constant multiples of functions can be pulled out in front of the integrals. So the antiderivative of c times f of x dx is equal to c times the antiderivative of f of x with respect to x. And again, we have the constant multiple rule and differentiation that matches this. So let's take a look at an example, and we'll see in this example why the plus c is important, why it has to be there, and how it can play into solving physical problems. So we have an object that moves on the x-axis. We're told that at time t, the acceleration of the object is given by a of t equals 4e to the 2t minus 6t squared plus 4 meters per second squared. Some additional information is given. We're told at time 0 the object is moving with velocity 4 meters per second and at that time is at the position 5 meters. The problem is to find where is the object at time t equals 5 seconds. So working from acceleration back to velocity and position is a very popular, common type of antidifferentiation problem. So we start with this. We know acceleration is the derivative of velocity. So it's also the case that velocity is an antiderivative of acceleration. So if we let v of t be velocity, we can find v of t by taking the antiderivative of a of t, or the antiderivative of the acceleration expression. Apply the linearity rules we learned earlier, that we can break this integral up along the sum and the differences, and likewise pull out multiplicative constants. So v can be found by doing 4 times the antiderivative of e to the 2t dt minus 6 times the antiderivative of t squared, and then plus the antiderivative of 4. So we can read the first 2 antiderivatives from the table on page 281. In fact, also the antiderivative of 4 is 4t. That comes from that 16th entry we included. So we'll take a quick look at the table here and see where we find these things. So the first term there was the exponential. We were dealing with e to the 2t, so the k was equal to 2. Of course, the variable is t rather than x, and we see from the table that this is going to become 1 over the constant k, 2, and then e to the 2t. Likewise, for the power, we have to integrate or antidifferentiate. Okay. This was a t squared, and according to the antiderivative rule, if we work with a power like x to the n, we add 1 to the power and divide by that new exponent. So this is going to become t to the 2 plus 1 divided by 2 plus 1, or t cubed over 3. You can check both these. You can take the derivative of t cubed over 3, see that you get t squared back, and likewise differentiate this 1/2 e to the 2t, and you do get e to the 2t back. And our 14th entry, constant, has antiderivative kx plus c, tells us that the 4 will become 4t. Again, the variable here is t rather than x. So we filled those things in over here and done a little bit of algebra. And notice now we've added the plus c at the end. Each of these antiderivatives we computed contributes a plus c, but since a constant plus a constant plus a constant is a constant, normally when you do such a problem, you just put in 1 plus c at the end, which takes care of all those constants at once. Now, we see that we can figure out what the c is, and this is where these so-called initial conditions become important. We have information about where this object is and how fast it's traveling at time 0. So use the fact that v of 0 equals 4 meters per second to find c, and that calculation is done down here. 4 is v of 0, and I know v up here, so I can plug 0 in for t and get another expression for v at 0. That's all written out down here. And that calculation gives us just 2 plus c, because these two terms here become 0. And we can then solve for c, and c is 2. With that, we can then go back up and update what we know about the velocity formula. And see velocity is given by 2e to the t minus 2t cubed plus 4t. and now plus 2 because we know c is 2. So this tells us the velocity of the object at any given time. Now from velocity we move back to position. Because v of t is the derivative of position, s of t, we conclude s of t is an antiderivative of v of t. So that's on the next slide. So s of t is going to be found by doing the antiderivative of v of t, and here we've just put in what we found out about v of t before, and then once again applied the linearity rules to break this up into a sum and difference of integrals of elementary functions, with the constants pulled out in front. We handle these antiderivatives the same way we did before with the aid of the table, and our result is this. As before, the 1/2, or rather the e to the 2t, antiderivative of 1/2 e to the 2t, the power rule, the t becomes t to the 3, t cubed becomes t to the 3 plus 1 over 3 plus 1, which is where this should have been a t to the 4th, not an x. That's where the t to the 4th comes from. And we handle the t to the 1st in a similar way, the constant term, and then once again a constant of integration. And so a result down here for the position function, e to the 2t plus minus 1/2 t to the 4th plus 2t squared plus 2t plus d. And once again, we know where the object is at time 0. It's at position 5. So we can write, making use of what we know about the velocity function up here, or the position function up here. We can write 5 is s of 0, and then if we plug 0 into what we know about the position function, we get this expression, and that reduces down to 1 plus d. And so once again, it's easy to find the constant d. D turns out to be 4. And if we put that 4 back in for d and then update our position function, we have a complete picture of the position of the object at any given time. So there is an expression of s of t, and notice again how the constants of integration, the plus c plus d, were taken care of by the initial, what were called initial conditions, the data that v of 0 equals 4 and s of 0 equals 5. Now we want to answer the question, the problem, which said where is the object at time 5? And that's one more computation. We can now just plug 5 in for t up in the position formula. And doing that gives this expression here. And we see the object's pretty far away. It's at the meter mark, 21,778. So this concludes our video. Please study up on those antiderivatives of elementary functions in your book. Don't forget to add the plus c, and watch for initial conditions, such as in this last example, to help you find the value of the constant should you need it.